Welcome to today's Geek Capsule. With the book Introduction to the Theory of Computation, we will explore the fundamental capabilities and, just as importantly, the limitations of computers. It is divided into three main parts, and we'll walk through each chapter step by step. Chapter 1: Regular Languages. This chapter introduces the most basic model of a computer, called a finite automaton. What is a finite automaton? Imagine a machine with an extremely limited memory, like the controller for an automatic supermarket door. It only needs to remember if it's in the open or closed state. It doesn't have a lot of memory, but it's very useful for certain tasks. This simple machine is a finite automaton. Key concepts. Regular languages. These are the languages, or sets of strings, that a finite automaton can recognize. Non-determinism. This is the idea that a machine can have multiple possible next moves from a single state. While this sounds powerful, the chapter shows that any non-deterministic automaton can be converted into an equivalent deterministic one that has only one next move at every step. So, for finite automata, non-determinism doesn't add any fundamental power, but it can make them easier to design. Regular expressions. This is a compact way to describe the strings in a regular language. For example, a regular expression can describe any string that starts with an A and ends with a B. This chapter shows that regular expressions and finite automata are equivalent in power. The pumping lemma. This is a special tool. It's a property that all regular languages have. If you can show that a language doesn't have this property, you've successfully proven that the language is not regular, meaning no finite automaton can recognize it. Main takeaway. The simplest computational devices, finite automata, recognize a class of languages called regular languages. Their power is well understood, and we have tools to prove exactly what they can and cannot do. Chapter 2: Context-Free Languages. Here, we level up to a more powerful type of language and machine. Key concepts. Context-free grammars, CFG. Think of these as a set of grammatical rules like you might have for English, but for defining a programming language. They allow for recursive structures, like an expression that can contain other expressions inside parentheses. The languages they generate are called context-free languages. Push-down automata, PDA. This is our next machine model. It's essentially a finite automaton with one crucial addition, a stack. A stack is a memory structure where you can only add or remove items from the top, like a stack of plates. This simple addition allows it to recognize the entire class of context-free languages. Equivalence. Just as finite automata and regular expressions were linked, push-down automata and context-free grammars are also equivalent in power. The pumping lemma for CFLs. Similar to the one for regular languages, this is a more powerful tool used to prove that a language is not context-free. Main takeaway. Adding a stack from memory gives a machine more power. PDAs and CFGs are perfect for describing the syntax of most programming languages, but like finite automata, they also have their limits. Chapter 3: The Church-Turing Thesis. This chapter introduces the Turing machine, which is the model for a general-purpose computer. Key concepts. Turing machine. This is a finite automaton with an infinite tape that it can read from, write to, and move back and forth on. It has unlimited and unrestricted memory. This model is believed to be powerful enough to perform any computation that any real-world computer can. The Church-Turing Thesis. This is a foundational principle, not a formal theorem. It states that our intuitive idea of what an algorithm is corresponds exactly to what a Turing machine can do. This thesis allows us to use the Turing machine as a precise definition of an algorithm. Decidable versus recognizable. A problem is decidable if there's a Turing machine that can solve it and is guaranteed to halt with a yes or a no answer. A problem is Turing recognizable if a machine will halt and say yes for any yes instance, but might loop forever on a no instance. Every decidable problem is also recognizable, but the reverse isn't always true. Main takeaway: the Turing machine is the accepted mathematical model of an algorithm and a general-purpose computer. It establishes the theoretical gold standard for what is computable. Chapter 4: Decidability. This is where things get truly mind-bending. The chapter explores the stunning fact that there are problems that are computationally unsolvable. Key concepts. The halting problem, ATM. This is the most famous undecidable problem. It asks, given a description of a computer program and its input, can you determine if the program will ever finish running or if it will loop forever? This chapter proves that no general algorithm can ever exist to solve this problem for all possible programs. Diagonalization. This is the brilliant proof technique used to show the halting problem is undecidable. In essence, you imagine a list of all possible programs, and then you construct a new program that is guaranteed not to be on the list by making it behave differently from every program on the list. This leads to a logical contradiction, proving the original assumption that an algorithm for the halting problem exists must be false. Unrecognizable languages. The chapter goes one step further to show that some problems are not even Turing recognizable. The complement of the halting problem is the prime example. Main takeaway: there is a hard, provable limit to what computers can do. Some problems are simply beyond the reach of any algorithm, no matter how clever or powerful. Chapter 5: Reducibility. This chapter introduces the single most important technique for proving that problems are undecidable. Key concepts. Reducibility. This is the idea of transforming one problem, A, into another problem, B. If you have a way to solve B, this transformation gives you a way to solve A. Proving undecidability via reduction. Here's the core idea. If you already know that problem A is undecidable, and you can show that you could use a solution for problem B to solve problem A, then problem B must also be undecidable. If B were solvable, it would mean A was solvable, which is a contradiction. Key undecidable problems. Using this method, the chapter proves that many other problems are undecidable, such as determining if a Turing machine's language is empty or if two Turing machines recognize the same language. The post-correspondence problem, PCP, a fun but undecidable puzzle involving matching strings on dominoes. It's very useful for proving other problems related to grammars are undecidable. Main takeaway: reducibility is the workhorse of computability theory. It allows us to build a whole family of undecidable problems, all starting from the foundational proof that the halting problem is undecidable. Chapter 6: Advanced Topics in Computability. This chapter is a deeper dive into some of the more advanced and elegant ideas in the field. Key concepts. The recursion theorem, a fascinating result showing that any program can be written to obtain its own source code and compute with it. It's the theoretical basis for self-replicating programs or computer viruses. Logical theories. The chapter explores whether truth itself can be automated. It shows that for some mathematical systems, like arithmetic with just addition, truth is decidable. But once you add both addition and multiplication, you get Gödel's incompleteness theorem. There are true statements about numbers that can never be proven. Turing reducibility. This is a more general type of reducibility using a concept called an oracle, an imaginary black box that can solve a problem in a single step. It helps classify problems that are undecidable into different degrees of unsolvability. Kolmogorov complexity. This concept defines the amount of information in a string as the length of the shortest possible program that can generate it. A string that is truly random is incompressible, meaning its shortest description is the string itself. Main takeaway. Computability theory contains deep and beautiful results that connect with logic, self-reference, and the very nature of information. Chapter 7, Time Complexity. Now we shift focus from what can be computed to what can be computed efficiently. Key concepts. Big O notation. This is the standard way to measure an algorithm's runtime, focusing on how it scales with the size of the input. The class P. This is the class of all problems that can be solved in polynomial time, which means the runtime is bounded by some power of the input size, like n squared or n cubed. These are generally considered the efficiently solvable or tractable problems. The class NP. This stands for non-deterministic polynomial time. A problem is an NP if a proposed solution can be verified efficiently. For example, finding a path in a maze might be hard, but if someone gives you a path, verifying that it's a correct solution is easy. P versus NP question. This is the million-dollar question. Does P equal NP? In other words, if a solution to a problem can be verified quickly, can the solution always be found quickly? Most computer scientists believe P does not equal NP, but no one has been able to prove it. NP completeness. The NP-complete problems are the hardest problems in NP. If you could find an efficient polynomial time algorithm for just one of them, you would have an efficient algorithm for all problems in NP, which would prove P equals NP. The first problem proven to be NP-complete was the Boolean satisfiability problem, or SAT. Main takeaway. The P versus NP question is the central open problem in complexity theory. The concept of NP completeness gives us a way to identify thousands of important problems that are likely intractable, even though we can't formally prove it yet. Chapter 8. Space Complexity. This chapter analyzes problems based on the amount of memory, or space, they require. Key concepts. PS space. This is the class of problems that can be solved using a polynomial amount of memory. Savage's theorem. A key result showing that any problem solvable with a polynomial amount of space on a non-deterministic machine can also be solved with a polynomial amount of space on a deterministic one. This means that, for space, non-determinism is not nearly as powerful as it seems to be for time. In short, NPS space equals PS space. The classes L and NL. These are problems solvable in logarithmic space, a very small amount of memory, on deterministic L and non-deterministic NL machines. NL equals co-NL. A shocking discovery in complexity theory. It shows that non-deterministic log space machines can solve problems just as easily as they can solve their complements, a property not believed to be true for NP. Main takeaway. Space is a distinct resource from time. We know that P is contained in PS space, which is contained in EXP time, problem solvable in exponential time. But we don't know if these classes are truly different. The NL equals co-NL result shows that our intuitions about complexity can sometimes be wrong. Chapter 9. Intractability. This chapter provides the tools to prove that some decidable problems are truly hard. That is, they require an enormous amount of resources to solve. Key concepts. Hierarchy theorems. These theorems formally prove our intuition that with more time or more space, you can solve more problems. For example, there are problems that can be solved in exponential time that provably cannot be solved in polynomial time. This gives us our first concrete examples of intractable problems. Relativization. This is a meta-mathematical idea that explores the limits of proof techniques. By introducing imaginary oracles, it shows that certain proof methods, like diagonalization, are not powerful enough on their own to resolve the P versus NP question. Main takeaway: we can definitively prove that not all decidable problems are efficiently solvable. The hierarchy theorems establish an infinite ladder of increasingly difficult problems. Chapter 10: Advanced Topics in Complexity Theory. The final chapter is a tour of several modern areas where complexity theory has had a major impact. Key concepts: approximation algorithms. When faced with an NP-complete problem where finding the perfect solution is too hard, we can often design efficient algorithms that find a good enough, near-optimal solution. Probabilistic algorithms. These algorithms use randomness as a tool. For some problems, like testing if a large number is prime, using randomness can lead to algorithms that are dramatically faster than any known deterministic ones. Interactive proof systems. This is a model of proof where a powerful prover tries to convince a skeptical but efficient verifier that a statement is true by exchanging messages. Astonishingly, the class of problems with interactive proofs, known as IP, is equal to P-space. Parallel computation. This area studies which problems in P can be solved dramatically faster if you have a huge number of processors all working in parallel. The class for these problems is called NC. Cryptography. Modern cryptography, which secures our online communications, is built entirely on complexity theory. Its security relies on the existence of one-way functions, functions that are easy to compute but very hard to reverse, which is directly related to the P versus NP question. Main takeaway: complexity theory is a vibrant, active field with deep connections to many areas of computer science and mathematics, leading to powerful new ideas in algorithms, proof systems, and information security. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.